My name is Sunil Takanaka-Fuller and my partner is Brian Takemoto, and for our final project we want to implement a coprocessor to the MIPS pipeline processor to support floating point arithmetic instructions. Our first goal is to implement add, subtraction, and multiplication single precision IEEE 754 format instructions. We then want to show the results on the D2 board in the 7-segment hex display. Here's the schematic for floating point addition. If we take a closer look, exponent A passes through here and exponent B passes through here. The most significant bits are zeros and they're subtracted A minus B and B minus A, and the result is passed through here. This is to determine the shift amount. Then this wire's most significant bit is the select line for here and here. So if the shift amount is positive, it passes through. If it's negative, it gets 2's complemented and passes through. These multiplexers are to choose the smaller mantissa to shift. The shift amount is passed through the shifter and it'll shift B, or B will pass through, or it'll shift A, or A will pass through. The results are then put into these subtractors or an adder, and whether or not it goes through here, here, or here is determined by these multiplexers. So basically the signs of the floating point numbers are XORed. If they're the same, then it's a 0. If they're different, then it's a 1. And if they're the same, the signal will pass through as an addition. And if they're different, we can tell which is the larger A by looking at the schematic here. So this will tell you whether or not A is larger, and we can do A minus B if A is larger, or B minus A if A is smaller. Then the output is passed to the normalization unit, where there's a bunch of multiplexers that determine whether or not we need to shift the mantissa. And then, as a future step, I would like to include rounding into the floating point addition unit. And once we accomplish rounding, then we can put the sign, exponent, and fraction into a value that is passed out as the sum. Here we can see that A and B are added correctly and outputted onto the sum line. Right now, my code can handle addition with no normalization and addition of different signs and normalizing the answer of that. So if the answer needs to be shifted to the left because it's too small, my code can do that right now. And for future steps, I would like to add normalization if there is an overflow, and also rounding.
Hey, this is Brian Takemoto, and this is my part of the video presentation. I'm going to take a look at the DE2 demonstration with the 7-segment display. And of course, I'm going to show my multiplier, which is part of the coprocessor for the floating point unit. So, since I'm at it with the camera, I'm going to start off with the DE2 presentation. It's a very simple DE2 presentation. What I did was that I used a simple MIPS code where I load the switch input values and output it to both the LED and the 7-segment display. So using binary numbers, we can start off with 1, 2, 3, 7. Very simple. So let's move on to the multiplier, because that is the biggest part of my role in this project. Alright, I will now discuss about the floating point multiplication. So the most difficult part about this part of the project is to multiply two large numbers efficiently, specifically the mantissas, which are 23 bits. With the implicit one, it is a 24-bit multiplication. So that is going to be a big challenge. I took the opportunity to study the Booth's multiplication algorithm, which will efficiently multiply the 24-bit numbers every 26 cycles. So it is very efficient versus the brute force tactic, which can vary from 15 cycles to maybe even 1,000 cycles. So the algorithm was translated into hardware on the whiteboard. As I was building this in the code, as you can see, I did notice some certain small details that I did not look at, and I did fix them. Not the biggest issue of the entire circuit, but this is the general idea of the circuit. So inputs are on the left, the registers to save the numbers or the accumulator. The middle part is the combinational logic that progress in the algorithm, and of course on the right side is the control unit for this particular multiplier, which takes 25 cycles to compute the number and 1 extra cycle to start it, because it has to receive the instruction from the instruction memory. In the simulation, I took two numbers, which are right here. I took 25.5 and 68.9, so that I have them inputted right here. And the result after 26 cycles is right here. And when you multiply those two numbers, you get 1,756.95. So if you take a look here, I put in 1,756, and this is the hexadecimal value, and it definitely matches this particular value. Thanks for watching.